Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Problem set for Lecture 104. Okay, problem number 1. Consider a parallel plate capacitor with a variable spacing of d between the two plates. For each of the following scenarios, determine how capacitance C, free charge Q, voltage V, and electric field E of the capacitor change. All right, so this applies to problems 1 through 4. I should have probably had that specified there. So number 1, we're going to consider the scenario where the capacitor plates are initially held at a distance d0 equals 1 millimeter, and the capacitor is fully charged by a 12-volt battery. Then the battery is disconnected, and the spacing between the plates is increased to 10 millimeters. Which of the variables C, Q, V, or E change as a result, and by what factor, and in which direction do they change? I know it's kind of long and wordy. I apologize for that. But let's see. Number 1. So let's start by specifying what does not change. So since the battery is disconnected, we know that the charge, Q, is fixed. So that means that Q new will be equal to Q old. Now since the electric field in a parallel plate capacitor is equal to E is equal to sigma over epsilon naught, which is then equal to Q divided by epsilon naught A, the area of the plates. And since Q is not changing and A is fixed, that doesn't change, the surface area of the capacitor plates, then that means that E does not change either. So E and Q, right, so we'll say E new equals E old. So that doesn't change either. However, V is equal to, the potential is equal to E times D, and since D changes, going from 1 millimeter to 10 millimeters, and E is constant, that means that the voltage must change. So we can write that V new equals E times 10, which is equal to 10 times V old. Also, C new, the capacitance, will be equal to the charge, which doesn't change, divided by V new, which is equal to the charge, divided by 10 times V old. So that's equal to the old capacitance divided by 10. So we can summarize this by saying the voltage increases by 10, factor of 10, and the capacitance decreases by a factor of 10. And so that would be the scenario for for number 1. All right, number 2, the capacitor plates are now held at a spacing of 10 millimeters, and a dielectric with K, the dielectric constant, equal to 10, is inserted between the plates, filling the space between the plates. Yeah, so we insert the dielectric material, it fully fills the space in between the plates of the capacitor, and so which of the quantities change, C, Q, V, or E, as a result, and by what factor and in which direction? Okay, so for 2, let's see. So Q is still constant, right? So Q new is still equal to Q old because we haven't hooked anything up to a battery. However, E being equal to the charge, surface charge density divided by epsilon naught times kappa, right? That's the electric field when you insert a dielectric in between the plates of the parallel plate capacitor. It goes from sigma over epsilon naught to sigma over sigma over epsilon naught kappa. So that means that E new is equal to 1 over 10 times E old, because kappa is equal to 10. The potential, V, is equal to E times D, with D constant, so V new is equal to E new times D, which is equal to 1 over 10 E old, which is equal to, times D, which is equal to 1 over 10 V old. What about the capacitance? The capacitance is equal to C equals Q over V. So C nu will be equal to Q over V nu, which will be Q over 10 times V old, which will be equal to C old over 10. So, to summarize for problem number 2, or did I mess something up here? It's 1 over 10, sorry, 1 over 10. Yeah, it's 1/10 V old, right? That's our result from here. So that makes this 10 times C old. There we go. So let's summarize that. The electric field will go down by a factor of 10. Because I could put semicolons here. The potential will also go down by a factor of 10, but the capacitance will go up by a factor of 10. And that's what happens when you put a dielectric material in between the plates of a parallel plate capacitor. It increases the capacitance by the dielectric constant. All right, number 3, the capacitor plates are initially held at 1 millimeter, and the capacitor is fully charged by a 12-volt battery. So we're going back to the beginning. We're back at like problem 1 again. So then with the battery remaining connected, so this time we don't disconnect the battery, the spacing between the plates is increased to 10 millimeters, which of the C, Q, V, or E changes, and by which factor and in which direction. So we're redoing the problem again, but this time we're leaving the battery connected. So 3. So this time V does not change, right? So let's V new equals V old. Because it's always connected to the battery, that's going to keep the potential the same. Since V is equal to E times D, then E new will equal V new, which is V old, just V, over D new, which is equal to 1 over 10 E old. Okay, what about the capacitance? Well, C nu is equal to epsilon naught A over D nu, which is equal to 1 over 10 times epsilon naught A over D old, which is just 1/10 of C old. Okay, so the capacitance changes. What about the charge? Well, this time, right, there was going to be a change in the charge. Before, in 1 and 2, it was always a constant. This time, the charge can change. So Q nu is going to be equal to V times C nu, which is V times 1 over 10 C old, which is equal to 1 over 10 Q old. So let's summarize this. The electric field goes down by 10. The capacitance goes down by 10. And the charge goes down by 10. You can contrast that with 1, in which the battery was disconnected. All right, number 4. The capacitor plates are now held at D equals 10 millimeters, and the battery is still connected. A dielectric with K equals 10 is inserted between the plates. So what changes, by how much, and in which direction? Okay, so number 4. So V and D are still unchanged. So V and D are unchanged. Okay. V is equal to E times D, and since D and V both don't change, right, E equals V over D, that means that E nu equals E old. So the electric field doesn't change either. Remember, in number 2, where the battery was disconnected, the electric field went down by 10. This time it doesn't change. What about the capacitance? The capacitance, which is equal to kappa times epsilon naught A over D. This implies that C nu is equal to kappa times C old, because A doesn't change, D doesn't change, and epsilon naught is a constant. So C nu is equal to 10 times C old. And finally, Q, the charge, Q nu is equal to the voltage times the capacitance, C nu, which is equal to 10 times V C old, which is equal to 10 times Q old. So, to summarize that, the capacitance increases by 10, and the charge also increases by 10. Q nu is equal to the voltage times the capacitance, C nu, which is equal to 10 times V C old, which is equal to 10 times Q old. So, to summarize that, the capacitance increases by 10, and the charge also increases by 10 when we insert the dielectric. Okay, number 5. Show that del dot E is equal to rho F, that's the free charge density, divided by epsilon naught kappa, starting from del dot D equals rho F. Okay, this is fairly straightforward. Number 5. So let me just remind you, D is equal to epsilon naught E plus P, polarization. This implies that del dot E plus P over epsilon naught is equal to rho F over epsilon naught. That's just Gauss's law. But P is equal to epsilon naught chi times E. So del dot E plus chi E is equal to rho F over epsilon naught. And I can factor out the E there, and that gives me that del dot 1 plus chi times E is equal to rho F over epsilon naught. But kappa is equal to 1 plus chi. And this implies that del dot kappa E, where I've just replaced 1 plus chi with kappa, is equal to rho F over epsilon naught. And that is pretty much the final result. That means that del dot E is equal to rho F over epsilon naught kappa. And that's what we sought out to show. I know these formulas can be messy sometimes, so it's handy to keep them written down somewhere so that you can refer to them quickly, because all of these definitions can be annoying sometimes. Okay, that's it for the homework this week.